This will be a look at section 7.1, where we're talking about graphing. And really, we're just kind of introducing graphing a bit. We're not going into too much detail right here, but hopefully you can see on your screen this coordinate system. That's actually what we call this when we have a couple of lines like this, one vertical line and a horizontal line, and we've got numbers on there. It's just a way really to share information. We call this the Cartesian coordinate system, and that is named after Rene Descartes, who was the one who came up with this idea. So it's the Cartesian coordinate system that we will mostly be using in this class. And we've defined some things like this strong horizontal line here we call the x-axis. And the strong vertical line with the numbers on it we call the y-axis. And that lets us relate things like y equals 4 minus x squared. Now we can graph that particular graph, but let's keep going and we'll talk about the coordinate system a bit more before we actually graph that. Notice that on the x-axis over here on the right-hand side, we have positive values. And on the left-hand side, we have our negative values. And also notice on the y-axis, above the x-axis, we have positive values. And below the x-axis are where we have negative values. So when we're plotting a point, what we'll do is we will say move over along the x-axis to a particular value and along the y-axis to another value, and we'll extend dashed lines from those axes, and where those intersect will be the point we're talking about. Now, we need to all come to agreement about how we're going to label that particular point. Well, this one had 4 on the x-axis and 3 on the y-axis. And so what we've decided to do is put in parentheses those two values, and we'll put the x value first and we'll put the y value second. So this is the point 4, 3. Recall that I said we put the x value first and the y value second, and it will always be that way. We call this pair of values an ordered pair. So whenever you're given an ordered pair, you can very quickly plot that ordered pair or put it on a Cartesian coordinate system by moving along the x-axis to the first number and then moving along the y-axis to the second number, and where those lines might intersect is where we would plot it. So if I were plotting the point, say, -5, 4, I need to recall that the -5 is the x and the 4 is the y. So I'll come along the x-axis to -5, which is right there, and along the y-axis to 4, which is right there, and then I might extend a dashed line from the 4 across and from the -5 up or down, wherever it takes to get that cross, and where those two dashed lines cross. That will be the point. In this case, that's the point -5, 4. And so we can pretty quickly plot any points that we need. Notice that up here in the top right, we have positive x values and positive y values. It will always be that case in this top right section, and we call that section quadrant 1. So quadrant is 1/4 of this ordered pair. It's kind of divided into quarters, And this is the first quadrant. The second quadrant is over here in the top left. And notice all of the x values over here are negative, but all the y values are positive. Down in the bottom left, that's quadrant 3. And down here we have negative x values and negative y values. Over here in the bottom right is quadrant 4, as you would imagine. And here we've got positive x values and negative y values. Using that, we can pretty quickly denote where a point will be. So if we had, say, -3, -2, because both x and y are negative, I know that is going to be in the third quadrant. So maybe I'll come over to -3, drop down to -2, and where those intersect will be that point. It's pretty easy to graph points that way, especially since we've got this border in place that allows us to very quickly graph or plot a given point. Now, I did mention that we had that one function, or the one graph of y = 4 minus x squared, and I said we would graph that. It'd be awful nice if we had a set of points that would go with that. But one nice thing about graphing is that we can always create what is called an XY table. When we have an equation with x and y in it, we can always do this. And what we'll do is we'll pick, say, a bunch of values that we want x to be. And then we will figure out from those x values what the corresponding y value would be. Remember back in a previous section when we evaluated expressions when x was equal to a certain thing. We'll do that same thing here. Y, since y equals 4 minus x squared, well, I'll just replace x with the x I picked and see what corresponding y value I get. Well, -2 times -2 is 4, so this becomes 4 minus 4, which is 0. So I now have the ordered pair, the x I picked and the y I got when I plugged that in. So -2, 0. I'll come over to -2 on the x and 0 on the y, and it puts me right there. Now let's plug in -1. 4 minus -1 squared. Well, we still have the 4 minus, and -1 times -1 is +1. 4 minus 1 is 3. So at -1, I have a y value of 3 right there. That was the point, the x I picked and the y value I got of 3. Let's plug in 0. Still have 4 minus, and now we'll have 0 squared. So that'll be 4 minus 0 times 0 is 0, and 4 minus 0 is 4. So I have the point, the x value I picked, and the y value I got when I plugged that in, and I've got 0 on the x, but 4 on the y, puts me up here. Now let's plug in 1. 4 minus 1 squared. So I still have the 4 minus, and 1 times 1 is 1. 4 minus 1 is 3. That gives me the point 1, 3. So 1 on the x, 3 on the y, puts me right there. And then we'll plug in the 2. So 4 minus 2 squared. I still have the 4 minus, and 2 times 2 is 4. 4 minus 4 is 0. So I have the point 2, 0. And you can see that I've created this collection of points, and now I need to connect those. Well, we'll try to connect them with a smooth curve. And if I were to keep going to -3, it would keep dropping down. Same thing if I came over here to a +3. So my graph looks something like that. It's a parabola. That's the shape that we get when we're graphing an equation with an x squared term in it as our largest exponent. And other classes get into more detail on those. But for now, just remember that no matter what equation we're given, if there's an x and a y, we can pick x values, plug them in and see what the y would be. And it gives us a set of points. And then we're playing connect the dots like we did when we were little kids. But it's pretty easy to graph an equation that way. We have another way to write these equations, and that's called function notation. So a function is what we're looking at here. And we will write those with a letter like F. That's pretty common. And what we'll do is we'll put in parentheses the variable that we will use to pick numbers for. And so in this case, it would be f of x. That means we have a function, we're calling it f, and the independent variable, or the variable that we'll pick numbers to plug in, is x. And we'll still write the other side the same. So f of x equals 4 minus x squared. That's the same thing as y equals 4 minus x squared. We're just highlighting that we have a function. And a function is a very particular term. It actually means for every x, I'm going to use x, but it really means for every independent variable, there is one and only one y. That's what a function means. So for every number we pick to fit in this variable, we will get only one output when we plug that in. So that means if I were to pick -7, for example, there would be only 1 point on the graph at the -7. If I picked -3, there would be only 1 point. If I picked -1, there would be only 1 point. So this kind of highlights that we have potentially a test that we can do to see if this is a function when we have the graph. If I were to draw a vertical line at x equals -1, and that's not super vertical, but we'll pretend it is, does it cross the graph in more than one place? And in this case, it doesn't. It only crosses in one place. How about 1? Only one place. How about 2? Well, 2.5, only one place. How about that -3 I talked about? It would only be one place. So if you can draw a vertical line, actually a whole set of vertical lines, and they only cross the graph in one place, that's proof that we had a function, because at the x value associated with that vertical line, it only has one y value. They call this the vertical line test. And it's a quick way to check if you have the graph of a function or not. We're just looking at the x values associated with every one of those vertical lines and seeing if it crosses at more than one place. So maybe I'll have a graph of something like this. That would be a cubic function, something like f of x equals, we'll say x cubed plus 2x plus 3, or something like that. So if we were to plot this, now that's not really the function that goes with this graph, but it would be something similar to that. So maybe I draw a bunch of vertical lines, and if I can draw any vertical lines that cross at more than one place, then it's not a function. But this one doesn't have that. Every time I draw a vertical line, it only crosses at one place. So this is indeed a function. Now, not all graphs have to be functions. It's perfectly fine to have a graph that isn't. For example, there's one that we really like, and it looks like that. I'm going to call it a circle, but in reality, it's more like a Skittle or an M&M. But notice I can draw vertical lines through here and cross the graph at more than one place. This is clearly not a function. And that's fine. We still like circles. We still want our pizza to be round. We want our wheels to be round. We like circles, but it's just not a function because we have more than one y value associated with each of those x's I drew. Now notice there are some places where I can draw a vertical line and it will only touch at one place. There are other places I can draw a vertical line and it doesn't touch at all. What we're really looking at is there anywhere I can draw a vertical line that crosses in more than one place. And in this case, there is. So not a function. Maybe we'll have something like this. Kind of pretty, maybe like a wave. All along in here, it's looking like a function. I'm not sure about right there, but maybe, yeah, that's looking functional. Oh, there's one, crossed 3 times. So that is not a function. Though it looked like a function up to there, as soon as I got to that point, it's not a function. And like I say, that's perfectly fine. We don't need to worry too much about that. It's just a way to define it. It allows us to do other things with math later on. One of the things that function notation gives us, let's go ahead and take a look at that one that I just made up. X cubed, I don't even remember what it is now, plus 2x squared plus 3 or something like that. But one of the things that function notation allows us to do is see exactly what we're plugging in to a function. So maybe I need to know what is f of -2. Well, notice what I've done here. I've replaced x with -2. So that being the case, I'll do exactly the same thing on the other side of the equal sign. And at this point, I like to rewrite the equation, but everywhere there is an x, I'm going to put a set of parentheses so that I can go back and type in to those parentheses this value I'm plugging into x. And let's see what we get. -2 cubed. Let's see what that is, because we haven't spent a whole lot of time talking about that. -2 cubed is the same thing as -2 times -2 times -2. Well, a negative times a negative is positive. We know that one. And that positive times this third negative gives us a negative. And then we look at the numbers. 2 times 2 is 4, times 2 is 8. So -2 cubed is a -8. Now let's keep going here. We've got a 2. -2 squared is -2 times -2. Negative times negative is a positive, and 2 times 2 is 4. And then we have our plus 3. So PEMDAS says I now need to do my multiplication. So we have -8 plus 8 plus 3. And now I can add those together, and I can do that left and right or any order I want. But I notice right here, I've got -8 plus 8. That actually turns out to be 0. So I'm left with just the 3. So f of -2 is 3. Or an ordered pair that I could use to graph is the ordered pair -2, 3. So maybe over to -2, up 3, and I happen to know that that spot on the graph, or that spot is on the graph of this function. We'll say that solves the function, or solves the equation, or satisfies the equation. Those are a couple of terms you may see as you're working through these functions and equations, is once you get an ordered pair that is on the graph, like we have here, it solves the equation or satisfies it. That can be helpful. All right, now let's take a look at perhaps a real world example that might help us make some more use out of this. It's always a little better, I think, when we can make use out of what we're doing. So what we have here is we're looking at stopping distances for cars at certain speeds. Notice the speed is down here in miles per hour. And we're comparing dry pavement to wet pavement. Well, as you know, it takes longer to stop on wet pavement. And that's why those blue lines are taller than the green lines, because stopping distance in feet is our y-axis. Notice we don't have x and y here, not really. We have speed versus stopping distance, and that's fine. Later, we'll look at a function where they did plug in x, and we'll see how to use that. Okay, let's see. There we go. I was pushing the wrong button for a minute. Over here on the right-hand side, what they've done is they've created this mathematical model by looking at the tops of all of these bars and then trying to draw a curve that fits along those lines or along those dots. So that's what they've done, and they tried to use an equation writer to come up with an equation that matches that, and that's what we have down here. That's an equation that matches that curve we see in the top right. So we have data on the left. These are real numbers from the real world, and we have a model on the right. They don't necessarily line up perfectly, but they'll be pretty close. So what they want us to do first is use the line graph, that's the model in figure 7.7, to estimate a car's required stopping distance at 60 miles per hour. So we'll come over here to 60 miles per hour, it's right there, and we'll work our way right up to the graph, which puts us at that point. And then let's work our way back over to the y-axis and see if we can figure out what the stopping distance is. Well, that looks a little higher than halfway between 300 and 400, but it's pretty close to half. My line isn't straight either. If I come back to the dot, that looks more like it is halfway between the two. So I would guess about 350 feet based on what we see on the graph. Now, let's come down to this model, this equation, which is the model of it. And we'll see, they tell me that stopping distance is f of x. So that's what we have over here on the left, stopping distance. And then they tell us that x miles per hour is the speed. So everywhere I see an x, that's the speed. Well, in our problem, we're going 60 miles an hour, so that's going to be the x. So what we're going to find is f of 60. That means I need to plug 60 in everywhere I see an x in that function. Oh, not a 0 there, that's a 4. And we'll definitely want to use a calculator at this point. So let's see. We've got 0.0875 times 60 squared, which gives me 315. That's a nice round number. And that was exactly what it gave me. I didn't round at all. Minus 0.4 times 60, which is 24, plus 66.6. PEMDAS tells me that now that all I have is addition and subtraction, I can work those left to right. So 315 minus 24 plus 66.6, and I get 357.6. And that would be feet, since it's stopping distance. So what we saw on the graph, on the line graph, was pretty close. We guessed 350, and when we plugged it into our equation, we got 357.6. They're really close, so it's about that distance. Now, if I were really worried about being precise for science, I would probably go out and measure a little more closely. But we also know that our speedometers aren't always 100% accurate. So we may be within what they call the margin of error and might be in the right spot here. Either way, we're pretty close. Now they might ask us, does this underestimate or overestimate? And so we would compare the value we got here from the model with what we might get if there had been a bar at 60. And usually if they want us to compare, there will be a bar where we're talking about. And then we can compare our value to the value they have on the bar chart. And if this modeled value is a little bit lower, then we would say the model underestimates. If the value we got when we plugged in the number was higher, we would say it overestimates, but it should be pretty close. And that's pretty well section 7.1. So give it a look, try the homework, see what you think. And if you have questions, definitely reach out. You know, I like to do math problems, so if you need me, let me know. Good luck.